A use for the for loop, besides creating vectors from user input, is to actually use vectors that have been created and analyze them. So it's going through a vector, but one element at a time. Remember that vectors are usually used to represent a collection of data points. They can be used to plot curves. But why would we want to go through a vector by looking at each element individually? Well, here are some applications. Maybe there's many maximums, so different bumps on your curve, and you'd like to find those. Or maybe you want to calculate derivatives or quantities at each data point, such as the acceleration in a vector. Or look at a curve that is weird. It doesn't have a function, but we still need to find the area. And that's the example that we will look at today. Now, to calculate the area of a curve is usually simple. If we have an actual function, a mathematical function, such as the sine of x, it will be the integral. But that's something you will learn in calculus class. And eventually, in advanced programming, MATLAB can actually do the integral. But what if the curve is not a function? What if the data points were collected from an experiment and we still need the area? Well, we can always bring it back to multiple slices, because we know how to calculate the area of a parallelogram. By cutting each piece of that function specifically, we might be able to approximate the data. So, if we split the curve into multiple parallelograms, there's 3 different types that we can easily see. The kind that's a perfect rectangle. We have the red, blue, pink, and blue. The kind that has a peak to the left. We have the black. And the kind that has a peak on the right. We've got 2 greens and 1 yellow. So there's 3 different types of parallelograms. So we might have to do an if statement to calculate each area separately. But do we really need to do 3 equations depends on the actual math. So let's look at the theory very quickly. The area of a plane rectangle is the width times the height. So in this case, we have 2 actual ways. The width is always x2 minus x1, but the height, we could use y1 or y2. For type number 2, we have a parallelogram. It still should be the width times the height. But let's finish the parallelogram first to somewhat resemble type 1. In that case, we'd add y1 and y2. That would be our height. Then we'd divide by 2 to come back to the original area. If you look at type 3, it's actually identical to type 2. So already right here we realize we only have 2 equations. But let's see what the difference is between the 2. The only thing that's different is the actual height. In one case it's just y1 or y2. In the other case it's the sum divided by 2. Try to compare type 1 and type 2 and 3. If you think about it, in type 1 we have y1 equals y2. So if we apply the actual equation overall, well, y1 plus y2 over 2 still simplifies to y1 or y2. So in reality, there is only one equation for this entire problem. So don't jump and code immediately without thinking first of the equations that you will have to code. Now, as far as the algorithm, trying to develop your process before you code, we'll have to go through our vectors. We have the vector of x's and the vector of y's. We need to calculate the area at each piece. So the first one, we'll talk about the 2 first elements. And then we'll move on to the second and third element, third and fourth, and so on. By the end, we should have all our slices separately. But by doing a running total, then we should be able to keep track of the total area. So, define our x and y values to plot. We realize we're going to go through our vector. So the best loop in this case is the for loop, since we know how many elements are in our vector. And for each slice, we'll have to find x1, x2, y1, y2, calculate the area for that particular slice, and then create a running total. Now remember that when we create running total, we need a starting point. So above the loop, we're going to set our total equal to 0. But as far as thinking roughly about our steps, that's as far as it gets. So, our x and our y have been defined. I've set up my entire algorithm. I've already coded the equation, since there's only one. And I'll try to finish the pieces that I know. Total area equals, that is the line for running total. So each time I will add on to the total by adding my slice. But remember that if we have a running total, we need an initial spot. To loop through the vector is the for loop. And we want to do this every time for every data point. So now I'm going to try working on these. x1, x2, y1, and y2. Now if we were simply working on the very first area, so the red one, we'd be using the one with the first two data points. So 0, 1 and 5, 5. In this case, x1 and x2 are on the top, y1 and y2 are on the bottom. But when we code, remember that we are referencing the values inside the vector. So we would have x of 1 and y of 1 for the first element, and x of 2 and y of 2 for the second element. But that's only applicable for the first area. But if I were to code these right now, as is, then every time I loop, I would be calculating the area of the red zone, the very first slice only. That would not give me the right area total. So that can't possibly be it, but we're getting there. So the idea is to generalize. Remember that the equation must be applicable to every slice. So imagine all of a sudden we're in the middle of the vector. I don't even know which value we're looking at, but we're looking at these two sets. So 5, 6 is still the x's, 3, 4 is the y's. And when I code, I need MATLAB to reference these. So instead of hard coding the index, I will use the variable k. If x of k is 5, then the 6 is x of k plus 1. MATLAB will automatically know that this means move on 1 up. And that will work for any area. So instead of a 1, it's k, and this is k plus 1. K plus 1. Now, to actually look at what k is, well, it's our usual control loop variable. K needs to go from one spot to another, but we're still not sure on that. That's the last part of our code. So, again, always go back to what you did on paper. Well, we had 9 data points. But when we did our process, we did it once for the first area, second, third, a 4th, 5th, and 6th time, 7th time, 8th time. But we didn't actually finish. We didn't do a 9th time since we would be trying to add k plus 1, and k plus 1 would make us exceed our dimension. On paper, we realize we loop 1 less than the amount of data points. 1 to the length of our vector minus 1. So we don't want to loop the entire amount of data points. We want to loop all the way up to the end, minus 1. And that's it. Notice how I've built step by step, always going back to what I was doing on paper. Build pieces by pieces. Last but not least, let's display our total area. So run. The total area would be 42. Now, the only way to check our answer would actually to do it by hand for every single data point. And technically we've already done it on step 5, but we didn't show it here. Another way to do this would actually be to code a function that you know. Remember that the area of the sine function would be 0. Just by looking at the curve, you notice that the area at the top would cancel out the area at the bottom. So let's code quickly the actual sine function. From 0 to 2 pi. And let's forget about our original data points. And let's do sine of x. We're expecting a 0. And we're getting a value that's very, very close to 0. Negative 3.17 times 10 to the negative 16. That's negative 0.3. That is equivalent to 0. So that's one way of testing our code, by doing something that we know. Even if we didn't learn integrals yet, we know by visually looking at the plot that the integral of sine of x from 0 to 2 pi is 0. That value is very, very close to 0. So I am confident that 42 is the right result. So here, this is the important part of the tutorial. We are looping through our vector. What we did within the vector was specific to the problem solved. But we are always referencing values in the vector using the k variable. And the k variable happens to be the loop variable. So let's conclude. The for loop is usually the one that is used to traverse vectors. The while loop can be used, but notice how everything in the for loop is set up perfectly. We tend to go from 1 to the length of the vector. Today we had to tweak the length because we didn't want to go overboard. To reference the actual elements within the vector, keep in mind it's what we've been doing. Vector name, and in parentheses the index. Again, today we had to manipulate the index to go k plus 1. You could do k minus 1, k plus 2, depending on the problem you're solving. The end value of the for loop should never, ever, ever be hard-coded. Notice I did not do for k equals 1 to 9. 9 would make me always use a vector of length 9, which wouldn't have worked just to test the sine function. So never hard-code that value. Keep in mind the vectors may be able to change at any time.